The cosmos teems with an unimaginable multitude of distant worlds. Out of the many thousands of exoplanets that astronomers have identified beyond our solar system, not a single one has proven more welcoming to humanity than our own Earth. Some of these planets are relentlessly scorched by the searing embrace of their nearby stars, while others are trapped eternally beneath thick shells of ice or bombarded by catastrophic levels of radiation. Yet amid this abundance of hostile places, a few worlds stand apart in striking ways. There exist planets whose surfaces are adorned with sweeping oceans and winding rivers. Their skies are painted with drifting clouds, and their atmospheres are alive with the tumult of rainstorms and thunder. It is possible that such worlds might, one day, become the birthplace of marvelous and singular forms of life, just as life once found its beginnings here on Earth. Today, we are setting out to explore several of these extraordinary planets.
Few would argue that life itself is anything short of miraculous, intricate, and deeply enigmatic within the vastness of the universe. Although humankind has dedicated many thousands of years to unraveling its mysteries, countless critical questions have yet to be resolved. Of these, perhaps the most profound is this: how common might biological life be beyond our home planet? At this moment, we cannot confidently determine whether Earth's biosphere is a one-of-a-kind marvel or the expected result of unbroken evolutionary processes. Unsurprisingly, the quest to uncover life outside our world stands as one of the most vital scientific endeavors. To identify the celestial bodies most likely to harbor life, researchers employ a measurement known as the Earth Similarity Index, or ESI. This index rests on two essential factors: the strength of gravity at the surface of a planet and its equilibrium temperature. According to scientists, these properties are pivotal in assessing how closely another world resembles Earth, and how conducive its environment might be to fostering life as we know it.
The ESI's greatest strength lies in its elegance and straightforwardness. When a new exoplanet is found, astronomers can typically estimate its orbital path, mass, and radius, figures sufficient to derive the core components of the index. However, despite its practicality, the ESI overlooks a range of crucial elements necessary for sustaining life. For this reason, we propose to introduce our own method of assessment, expanding upon the ESI by incorporating several additional significant factors. One such factor is the activity of the host star. It is well established that the frequent flares and ejections of stellar matter, especially from red dwarfs, can wreak havoc on the atmosphere and radiation environment of nearby planets. Still, red dwarfs are often seen as more suitable than massive stars, like Sirius or Vega, whose brief lifespans and intense emissions leave scant opportunity for life to emerge. The optimal environments are offered by orange and yellow dwarf stars, including our own sun. Another factor to consider is the likelihood of tidal locking, which is tied to how close a planet orbits its star. Planets that travel too near their sun often present only one face toward it, resulting in extreme temperature contrasts between perpetual day and endless night. Conversely, planets situated too far from their star fall outside the so-called habitable zone, severely diminishing the prospects for life to arise.
The planet's type and elemental makeup must also be weighed, since the emergence of life demands a specific blend of chemical elements and a variety of surface features. These prerequisites are generally found on solid, rocky planets or on super-Earths. In contrast, many Neptunes are devoid of stable surfaces, and water worlds may lack key ingredients. Collectively, the parameters we have outlined allow us to paint a comprehensive picture of just how suitable a given exoplanet might be for nurturing life as we imagine it.
Within this framework, Earth stands out as an exceptionally appealing reference point, naturally serving as the standard by which other celestial bodies are measured. In contrast, Mars, even though it boasts the highest similarity index to our planet within the entire solar system, is burdened by several clear drawbacks. The red planet is much too frigid, possesses insufficient mass, and suffers from a severe scarcity of water. Venus, while superficially resembling Earth, is rendered inhospitable by extreme heat, a direct result of its intense greenhouse effect.
Although many of its characteristics fall within favorable ranges, the planet's blistering temperatures overshadow all its positive traits, making it unsuitable for life. As a result, no planet in our solar system is sufficiently akin to Earth to be deemed truly hospitable for living organisms. Yet, beyond the confines of our solar neighborhood, astronomers have already identified more than 5,000 exoplanets orbiting distant stars, and a number of these worlds share notable similarities with our own planet. Among the nearest of these is an exoplanet called Gliese 1002b, which lies a mere 15.2 light-years from Earth. In 2022, scientists discovered this world using the radial velocity method, a technique especially effective for detecting relatively nearby exoplanets by observing the subtle wobbles of their parent stars caused by orbiting bodies. Gliese 1002b orbits a faint red dwarf star known as Gliese 1002. This star is quite small. Its radius is only 14% that of our Sun, and its mass is 8 times less than our stars. The surface temperature of Gliese 1002 is just 3,000 Kelvin, or about 2,730 degrees Celsius, making its luminosity exceptionally low, around 700 times dimmer than the Sun. Unusually for its class, this red dwarf is relatively calm and stable. Because of its low brightness, the habitable zone surrounding Gliese 1002 is extremely narrow. However, Gliese 1002b is positioned right near the outer edge of this zone, making it a promising candidate for habitability. Observational data indicate that this exoplanet completes an entire orbit around its star in roughly 10 Earth days, meaning its orbital radius is very small, approximately 0.046 astronomical units. The planet's close proximity to its star, it is likely tidally locked, always presenting the same hemisphere to Gliese 1002. The amount of energy Gliese 1002b receives from its parent star is about 1.5 times less than what Earth gets from the Sun. As a result, its average surface temperature might be around 230 Kelvin or 43 degrees Celsius below zero. Interestingly, this is just a bit warmer than Mars, thanks to tidal locking and a potential greenhouse effect. This suggests that liquid water may exist on the planet's surface, opening the possibility for life to emerge, at least for certain Earth organisms that can endure such extremes. Further calculations reveal that Gliese 1002b is 8% more massive than Earth, with a radius just 3% greater than our own planets. Using this data, it is easy to calculate the gravitational acceleration at its surface, which is nearly identical to what we experience here on Earth. Altogether, these findings point to Gliese 1002b being a rocky world with much of its surface blanketed in ice. Owing to its close similarity to Earth in terms of size, it has a rather high Earth Similarity Index of 0.86, and in our comparative framework, this world would appear as follows. Climate models further indicate that the side facing the star could receive enough warmth to maintain a liquid ocean, complete with archipelagos or even full continents. Furthermore, tidal forces generated by the nearby star may heat the planet's interior, making the existence of a hidden subsurface ocean beneath the ice, even on the planet's dark side, a real possibility. By the way, Gliese 1002b is not the sole planet orbiting its star. Its discovery came together with another celestial body, named Gliese 1002c, which lies a bit farther out, precisely at a distance of 0.074 astronomical units from the system's center. This exoplanet completes a full orbit around its star in just 21 days, and its mass surpasses Earth's by roughly 36%. Remarkably, Gliese 1002c receives 4 times less energy from its star compared to what our world gets from the Sun, leaving its surface temperature quite chilly at approximately 182 kelvins or 91 degrees Celsius below zero. Utilizing an earlier established model, this exoplanet would appear as follows. Scientists believe that the environment on Gliese 1002c might closely resemble the conditions found on the moons of Jupiter or Saturn. The planet's considerable mass could fuel heightened volcanic activity, possibly leading to the creation of an underground ocean filled with warm, salty water enriched by various chemical compounds. Theoretically, such an environment might allow life to arise, perhaps in highly unconventional and unexpected forms.
Among the vast array of known exoplanets, some are significantly warmer and more hospitable. One such example is planet K2-72e, located 217 light-years away. This world encircles a small red dwarf star that is roughly 4 times less massive than our Sun. The star's radius measures about 0.33 of our solar radius, and its temperature remains relatively modest, reaching 3,360 kelvins, which is nearly 3,100 degrees Celsius. Observations from the Kepler Space Telescope revealed that this exoplanet transits its star every 24 days, indicating that its orbit is very close, in the vicinity of 0.1 astronomical units. This suggests the planet is situated within the habitable zone and is a promising candidate for life. Data indicates that K2-72e may be tidally locked or perhaps in orbital resonance, similar to Mercury. Despite its star's faintness, this exoplanet absorbs 11% more energy than Earth does from the Sun. If K2-72e possesses an atmosphere akin to ours, its average surface temperature would hover around 295 kelvins or 22 degrees Celsius above zero, slightly warmer than Earth. However, should the planet be tidally locked, it is likely to experience dramatic temperature swings between its daylit and night sides. Additionally, it is important to note that its host star, like most red dwarfs, is unstable and prone to frequent flare-ups, releasing massive bursts of stellar matter into space. Such activity can threaten the atmosphere and surface of surrounding planets. Calculations show K2-72e has a diameter 29% greater than Earth's and carries roughly 2.2 times Earth's mass. This allows us to estimate its surface gravity, which is about 32% higher than what we experience. Taking all available information into consideration, it seems probable that K2-72e is a rocky super-Earth with liquid water and a substantial atmosphere. Its Earth Similarity Index is quite high, standing at 0.87, and according to our model, the planet would appear as depicted. Worlds of this category are expected to possess a broad spectrum of chemical elements, and their landscapes are typically smooth, ideal for the emergence of life. Of course, the frequent stellar flares pose a genuine danger to the atmosphere, but a robust magnetic field could conceivably deflect charged particles from the stellar wind, while the oceans would shield living creatures from harmful radiation. If so, K2-72e might display breathtaking auroras, even more spectacular than those on Earth. As for the planet's potential biosphere, it would probably differ greatly from ours. The altered light spectrum might prompt native plants to utilize alternative pigments for photosynthesis, possibly giving their leaves a purple or reddish tint. Furthermore, the threat posed by excessive radiation could deter many life forms from ever setting foot on land. On the other hand, such intense conditions might actually drive the evolution of specialized defenses, including thickened protective layers or unique cellular adaptations. Remarkably, similar traits can be found in certain hardy terrestrial creatures, like tardigrades, archaea, and a selection of fungi. Meanwhile, aside from this particularly alluring world, astronomers have identified 3 more planets within the same system. 2 of these, named K272b and K272c, orbit extremely close to their parent star, and each one slightly surpasses Earth in size. Scientists suspect that due to the star's powerful radiation and stellar winds, both planets have lost any semblance of an atmosphere, leaving them bare and inhospitable, much like Mercury. The third, K272d, is thought to resemble Earth in size and travels along an orbit with a radius of roughly 0.08 of an astronomical unit. It completes a circuit around its star in about 15 days, situating it close to the system's habitable zone's inner boundary. Given its proximity and high surface temperatures, Conditions on K272d are probably reminiscent of those on Venus, making the emergence of life exceedingly unlikely. Nevertheless, research into this intriguing system continues, promising new discoveries in the years to come. Curiously, all the planets discussed here share a similar scale with Earth, yet life as we know it is remarkably adaptable, able to thrive under a vast range of circumstances, even enduring powerful gravity that can be found on massive worlds.
If we journey approximately 1,800 light-years away from our solar system, we encounter a yellow dwarf star whose characteristics closely mirror those of our Sun. This star, named Kepler 452, is a main-sequence sun, only about 3 7/10% more massive and 11% larger than our own. In the year 2015, astronomers made an extraordinary discovery, an exoplanet called Kepler 452b detected using the transit method. Precision observations revealed that this planet sits at a distance of 1 400th astronomical units from its star, completing a full orbit in 385 days.
Its position within the system makes it highly unlikely that the planet is tidally locked, which is an encouraging sign for habitability. Current data suggest that Kepler 452b has a mass about 5 times that of Earth, and its radius is roughly 1.5 times greater than our planet's. As a result, gravity on its surface is estimated to be 2 2/10 times stronger than what we experience on Earth. Such formidable gravity would likely help the planet retain a thick atmosphere and could smooth out its terrain, creating many shallow temperate seas. These conditions are widely considered ideal for the origin of life, though the gravity would pose a significant challenge for human visitors. It is also known that Kepler 452b receives 10% more stellar energy than Earth collects from the Sun, and it lies squarely within its star's habitable zone. Calculations indicate that its average surface temperature hovers around 300 Kelvin, or 27 degrees Celsius, which is 11 degrees warmer than Earth's average. This suggests that Kepler 452b's climate might resemble that of Earth during the Mesozoic era. However, depending on its atmospheric composition, these temperatures could be hazardous and might hasten a runaway greenhouse effect, potentially causing the planet's oceans to evaporate entirely. Some theories propose that a similar process transformed Venus several billion years ago. Considering all these factors, it appears probable that Kepler 452b is a rocky super-Earth, abundant in diverse elements and minerals. Due to its heightened levels of radioactive materials, it is believed that such a world would experience intense volcanic and tectonic activity, while its strong gravity would suppress the development of towering mountains and deep chasms. Simultaneously, the proportion of land versus ocean covering the surface of Kepler 452b is expected to differ from what we see on Earth. As a result, there is a significant possibility that this exoplanet could be an endless sea adorned with scattered island chains. For a moment, let us set aside mathematical calculations and attempt to envision what life might look like on such an extraordinary world, one that mirrors Earth in certain ways, yet diverges so dramatically in others. The scene unfolding before us would be truly breathtaking. The likely presence of vast, shallow, sunlit waters hints at a remarkable diversity of aquatic creatures, ranging from the tiniest organisms to the most majestic beings. On the rare stretches of land, we might find robust trees with thick trunks and sturdy, broad-leaved plants. Given that the parent star's light spectrum closely resembles that of our own sun, the leaves and stems of native plants would probably exhibit hues familiar to us, shades of green, or perhaps tinged with blue. We might also anticipate a population of small animals, their bodies fortified with strong bones and powerful muscles. Evolution could take a different path too, favoring beings with hard external shells, much like the arthropods inhabiting Earth. The question of flight, however, divides experts. Some exobiologists argue that the planet's substantial gravity could prevent flight altogether, while others contend that a denser atmosphere might actually make flying easier. Regardless, decades, if not centuries, of research still lie ahead before we can determine with certainty whether this planet can support life. Each year, humanity uncovers hundreds of new exoplanets. Some are inhospitable and perilous, while others bear an uncanny resemblance to Earth. Yet, for all our discoveries, these distant worlds remain beyond our reach. For now, Earth stands as our sole sanctuary, and it is imperative that we seize every opportunity to safeguard it. Every stride in progress leaves its mark upon our home, and it is impossible to predict precisely when these changes might become irreversible. Let us continue to stay connected and mindful of our responsibility.